All right, let's jump right into night rotational set 2. And I always think it's a good idea to remind you can pause at any point and see if you can finish the problem from where I am, or zoom through and just see how I did it. All right, we have three identical coins as shown in the image to the side. Determine the x and y coordinates of the center of gravity. Well, I'm going to make a prediction before I even jump in. First of all, we're going to separate it and find the x center of gravity and the y center of gravity. And then that'll tell us where in space our center of gravity is. And right off the bat, if we look at just the x's, we have 2 at the 0 position and 1 at the 10 position. So it's probably going to be left of the halfway point. And vertically, very similar. Okay. Vertically, we have 2 below the halfway point and 1 above it. That's going to shift the vertical center of gravity down, which means our ultimate center of gravity is, if this is dead center 5, 5, it's going to be down here-ish. And recall that to find the center of gravity, it's the position times the mass. For all of them added together, so x1, m1 plus x2, m2, blah, 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 all the way up to the final coin. And then to find just the position, just the x, we divide it by the total mass, or the sum of mass. So you can do this one of two ways. If you don't know the mass, you can plug in m as the mass. Or since they're all the same mass, you can assume it's whatever mass you want. To try to find it, you could assume a mass of 1. I'm not going to take that shortcut in this solution. I am going to just make the assumption that they're all of mass m, which they are. There's nothing inaccurate about that assumption. I'm also going to be converting everything to meters just in case I would ever have to convert these. That way I don't make a mistake. So I'm going to call this coin A, B, and C just so I keep it straight while I'm talking about it. So the x position of A is 0, so 0m is 0. For B, x is 0.1 times m, plus for coin C, and I'll put those above, it's 0 times m. And then we divide out by our total mass, which is 3m. And then you're going to get 0.1 m over 3, which is going to be 0.03, or 0.033, because the m's will cancel. Meters, so our x position is at the 3 centimeter mark. And our y center of gravity is the exact same equation, except we replace our x's with y's. So let's go through and do them again in order of coin A, B, and C. For A, the x position is, or the y position is 0, so that one's going to be 0m. For B, it's 0, so that's also going to be 0m. And for coin C, the vertical position is going to be 0.1 m. And then divide it by the total mass, which again is 3m. And we're going to end up with the exact same equation we had here, which means we're going to get the same y value as we had an x value, so 0.033. Oops, I don't know how I popped that m on there. So our position, oh, meters, not m, meters. Wow, that's confusing if I'm not cautious. So your total position, or your xy coordinates, should be 0.033 and 0.033, and both of those are in meters. 18. Solid hoop sits on top of a solid cube as shown in the figure to the right. How far above the table's surface is the center of gravity? Well, I'm going to call this block A and this cylinder B. And it doesn't matter about the shape. All that matters is if it's a uniform density object, we can assume that the center of mass is here, just like the center of mass of Earth is at the core. So if we're trying to find how far above the table's surface, we're looking for the vertical center of gravity. And I guess that would be center of gravity subscript y, but I like this better. So if this whole thing is 5 centimeters, that means its vertical position is 2.5 centimeters, or 0.025 meters. Similarly, this one's going to be 5 plus another half of 5, or also 0.025 meters, but plus the half from this height, so half plus another 2.5 is 0.075 meters. Or you could have done this in centimeters, 7.5 cm and 2.5 cm. In fact, since I did the first question with conversions, I'm going to do this one without conversions. Why not? Show you that they both work. Position times mass, or the sum of, it's the sum of position mass products divided by the total mass. And I worked through that in question number 16 if you want me to show you what I mean by that. But 2.5 times 800 grams. Ooh. So our units are going to be wonky. We're going to get grams centimeters for our unit product, or our derived unit for this, plus 7.5 times 400 divided by the total mass, which is 1200. And plugging that into our calculator, we're going to get 4.17 centimeters, because gram is the unit that's dividing out, so we're left with only centimeters. So you can do that. Just be very cautious with the units that you choose, or pay attention to what units you've carried through and what units you've crossed out. So if you have grams, centimeters in the numerator and you're dividing by grams, you're going to be left with centimeters. So absolutely feel free to do that. Just be cautious. 19, we have a 2 kilogram uniform horizontal rod from the side. What is the gravitational torque about the point shown? So that means that this is our pivot point. And you can approach this 2 different ways. Number one, you can break this up into 2 rods and say, okay, well, this rod's being pulled down this way, and this rod's being pulled down in its center of mass, which would be half of 75, and this one would be at 12.5 centimeters from the pivot point. This one would be trying to rotate it counterclockwise, which would be negative, and this one would be trying to rotate it clockwise, which would be positive. But the much simpler way is, again, we can treat it all as a single solid object and say, hey, this whole rod is being pulled down in its total center of mass, which is at the 50 centimeter mark. Which means it's going to be 25 what did I just do? 25 centimeters from the pivot point. And I'll draw that here. 25 centimeters, because we use 25 plus another 25 gets us to that halfway point. We know the mass is 2 kilograms. Mass equals 2 kilograms, which means the force of gravity is going to be 20 newtons. And we want to know the torque. Well, there's only one torque. So net torque is the sum of all torques, which is just going to be the torque of the board, which is going to be the radial arm of it times the force times sine theta. But again, theta is perpendicular to the radial arm, so this is going to become 1, and we just are left with the product of the radial arm and the force. I am going to convert centimeters to meters just because we're multiplying by another unit of meters, or I mean another unit that has meters within it, because force is a newton, which is a kilogram meter per second squared. And you don't want to mix centimeters with meters. And if you're ever unsure, just stick with the standard SI units and you'll never make a mistake. So 0.25 times the force, which is 20, and you should get 5 Newton meters. And because that's going to try to rotate it clockwise, that's going to be negative 5 Newton meters. 20. 4 meter long, 500 kilogram steel beam. Thank you. 4 meter long, and mass is 500 kilograms. Steel beam has been bolted to a new building, so I'm going to say, hey, this is our new building. It's bolted here. In fact, maybe it's bolted to the side of the building? Sure, why not? A 70 kilogram construction worker stands at the far end of the beam. In fact, I'm going to put the mass of the beam inside the beam just so I don't make a mistake. What is the magnitude? Oh, magnitude, which means that that negative sign should not be there, of the torque about the point where the beam is bolted into place. So we have 2 torques. We have, or rather, we're going to label all of our forces, right? You could say there, not you can say, there is a normal force or an applied force or tension force, some force where the bolt is holding the beam upward on the left side. So there is a normal force there. We have the force of the beam here, and we have the force of the construction worker here. What is the magnitude of the torque about the point? So we're trying to find the total torque or the net torque, which is going to be torque normal plus torque board plus torque construction worker. And as always, I'm going to put it in my zeros, positives, and negatives. Because the radial arm of the normal force is 0, the torque of it's going to be 0. It's not contributing a rotating force. It's not torquing the board. The board, we can assume it's a uniform board, or we can assume because it's a uniform board that its center of mass is at the halfway point or the 2 meter mark. So 2 meters would be the radial arm. And the force would be the weight of it, which is 500 times 10, or 5,000 newtons. And, oh, I forgot to put in all my positives and negatives. This one's going to be negative because it's rotating because it's rotating clockwise. And the construction worker, actually, he's also trying to rotate it clockwise. So they're both going to be negative. The radial arm of the construction worker is 4 meters because he's at the end of the board. His weight is going to be 700 newtons, or rather he's going to push the board down with 700 newtons of force. So we're at negative 10,000 minus 2,800. Let me plug that in because it's far enough off that I don't want to make a mistake. Oh, 12,008, yeah, negative 12,800 Newton meters of torque. Fantastic. 21. Oh my goodness! Magnitude, 12,800 Newton meters. I still almost forgot. An athlete at the gym holds a 3 kilogram steel ball in his hand. His arm is 70 meters long, so let's put him here, and let's just make him a stick figure, so that way we can see this is the point of rotation. And we have the ball here. His arm is 0.7 meters, or 70 over 100. And has a mass of 4 kilograms. Ooh, so let's give his arm some thickness. We have a good 4 kilogram arm. And what is the torque on his shoulder if he holds his arm straight to the side, parallel to the floor? Well, that's what we have in image A. So we have 2 torques, 2 rotational forces about this pivot point of his shoulder. We have the torque of the arm, or rather the force of the arm, that will create a rotational torque. And we have the force of the ball. Do we know the mass of the ball? Yeah, 3 kilogram. And let's put some fingers on this. There we go. And again, force is mass times gravity, so this is going to be 4 times half of 0.7, or 4 times 35 centimeters, because we can assume that it's being pulled down in the center of mass, and the force of the ball is going to be 3 times 10, or 30 newtons. So they're both at 30 newtons. So now let's find the total torque, which is going to be the torque of the arm plus the torque of the ball, which is going to be 1.4. Oh my goodness, I already did that. This should have been 40. Goodness gracious, I'm sorry, that's 40 newtons. I was jumping the gun. So 40 times 0.35. Did they say magnitude? Magnitude. So we are going to take the absolute value, but I'm still going to put in my negatives and positives, because if they subtract from each other versus adding to each other, that's going to give you a different result. Well, they're both in the same direction, so they're both going to be negative. So even though it says magnitude, don't take the absolute value until the end, so you don't make that mistake. Plus force times radial arm, 0.7. So this is going to be 2.1. This is going to be 140? No. 14. So 14 and 2.1. Let me make sure I did that right. 40 times 0.35 plus 30 times 0.7, which is 35. Wait, no, that can't be. Oh, the total answer is 35. So what's 30 times? Oh, 21, not 2.1. 21, that's why. So negative 14 minus 21 is negative 35, but they said magnitude, so 35 Newton meters. For part B, we have the exact same thing. So I'm actually going to cheat and copy my image and paste it over here. Oh, we can line them up at the exact same height. That's fantastic. Let's get rid of this, rewrite that. 40, except now it's 45 degrees below the horizontal, so we are going to need to include sine theta in this. And let's actually make this smaller just to give me a little bit more room, since we've already finished that. And then we'll move this guy over. Don't know how this is going to work. Hey, that actually worked. Cool. Cool. I am going to have to rewrite my forces, but that actually worked surprisingly well, because gravity always pulls things straight down. So we have this thing pulling down. Again, it's still being pulled down with its weight, the force of the ball, which is 30 newtons, and the force of the arm, which is 40 newtons. But we need the theta between the radial arm and the force. And this is where the geometry kind of comes into play a little bit. This is a 45-degree angle, which makes this, well, if this is a 90-degree angle, we have 90 plus another 45, which is 135 degrees. So let's get to work on our net torque. And both of them are still trying to rotate it clockwise, so they are still both going to be negative. So negative torque of the arm minus torque of the ball, which is negative RF sine theta for each. The radial arm is not going to change. It's still going to be 0.35 for the arm times 40 times sine of 90 plus 45, or 135. And that angle is actually going to be the same for both of them, because we're still going to have 90 plus another 45. So minus 30 times 0.7 times sine 135. And I'm just going to plug this into the calculator so I don't make a mistake like I did on the last part. And I get negative 24.7 Newton meters, but again, they did say magnitude. So I'm going to take the absolute value of that and get 24.7 Newton meters. '22. Oh, this is the last one. That was fast. We have a 2-meter long, 15 kilogram steel beam in the figure. It's hinged at its left end. It is falling, rotating clockwise under the influence of gravity. Gravity's pulling it down. And it shows its positions at 3 different times. What is the gravitational torque on the beam about an axis through the hinged end when the beam is at position A, B, and C? Well, this is, I think, the easiest question, especially after doing the other ones. We're going to do RF sine theta. And the only tricky part about this is making sure you get your angles right. So I'm actually going to draw them just so I don't make a mistake. All right, so this is our pivot point, and this is a 20-degree angle, and again, we can assume that the force is at the center of mass, straight down. So we need to find this angle theta, the angle between the radial arm and the force. Well, if this is 20 and this is a right triangle, this is 90, this has to be 70 degrees. So torque for A is going to be RF sine theta, which is going to be the case for all 3 of these. They're all going to be RF sine theta. So for A, it's going to be, well, 1 meter is the radial arm because half of 2 is the halfway point of the board. The force is always for all 3 of them. The weight of the board isn't changing, so it's always going to be 15 times 10 or 150 newtons. And sine of 70 degrees for this first one. That's all that's going to change for any of these. So then plugging that in, we get 150 sine 70. And I get 141 Newton meters. But it is rotating it clockwise, so I should have been more careful. Negative 141 Newton meters. For B, the radial arm is here, and the force is here. So this is going to be sine 90. 100% of the force is being used to rotate it, so sine theta is going to be 1. So for B, we're still going to do RF sine theta, where R is 1. This is negative because it's rotating clockwise. The force is still 150. Sine theta becomes 1. And your answer for that is negative 150 Newton meters. And for C, again, I don't want to make a mistake, so I'm going to draw it cautiously. It's at the 45-degree angle. So this is 45 degrees, and I guess this would also be 45 degrees. And this is our force. And this is, I'll change colors. This is our radial arm. So what is the angle between those? Well, if this is 45, then this is also 45, which means this is 45 plus another 90 because this is a right angle. So this is, again, a 135-degree angle for this whole green arc between the radial arm and the force. So RF sine theta, negative 1 times 150 times sine 135. And I get negative 106 Newton meters. I hope that helped. I hope you got a lot out of it. And I know it's been on everyone's mind, but I'm sure you guys heard about the little donks in the local area all getting sick um, because something went wrong with the carrots and they all started choking. Uh, and I guess every one of them is a little horse. I hope you enjoyed that, and I will see you in the next one, and have a great day. Bye.